Today we're going to do 4.7. This is, oh yeah. This is Lobito's rule. Lobito, looks like Lobito, sort of, but it's Lobito. Lobito was a nobleman who was interested in mathematics, and he hired Bernoulli. He said, hey, this new calculus thing sounds pretty cool. If I pay you 300 francs, will you come to my house every Thursday? Doesn't have to be Thursday. And teach me calculus. And Bernoulli said, sure. And Lobito had a little catch. He said, well, also if you discover any interesting mathematical nuggets, I want you to tell me before you tell anybody else. And so Bernoulli did this, and Lobito wrote one of the very first calculus books. And it was popular, and it was a good book from his education from Bernoulli. And in the beginning, he thanked Bernoulli quite a bit. But one of the things that appeared in this calculus book was the thing that we today call Lobito's rule. And of course, this is really Bernoulli's discovery. So Lobito gets maybe a scolding from history for having his name on this thing that we teach, many people, and it's really Bernoulli's. But maybe Lobito did a good job because, he wrote the calculus book that taught a lot of people. I don't know. That's my lack of insight for today. All right, so what is this Lobito's rule? Well, remember limits, right? We did limits at the very beginning, and they were kind of complicated, right? Well, here's the deal. If you have a limit, okay, if you want a Lobito's rule, and I always forget where I just want to spell it Lobito. T-A-L rule. It basically does something like this, If you have something like you want to compute the limit as x goes to a of f of x over g of x. We can do this really easily if f of x and g of x converge to something. However, there are lots of problem times. All right, so if the limit of f of x as x goes to a equals the limit as x goes to a of g of x, and if this is equal to 0 or plus minus infinity, and it doesn't matter if one could be plus infinity, the other one could be minus infinity. The key thing here is that, look, if g of x goes to 0, then we have a problem, right? Because then we're dividing by 0, and we can't really use our limit laws. If both go to infinity, we still have a problem, all right? And so Lobito's rule allows us to evaluate limits when they would ordinarily be problematic. Okay? Oh, and we need to know, and then the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f prime of x over g prime of x, provided this exists, if this exists. And so the idea here is, hey, if you can't compute a limit because the denominator and the numerator go to 0, or they both go to positive or negative infinity in either way, then what you do is you take the derivative of the numerator and the derivative of the denominator, and you see what happens, and maybe that will help out. All right, that's the goal, anyhow. So I'm going to do an example. I'm kind of a, Okay, so there's a list of basically forms. There's a list of things that you should be watching out for to use. Now, the biggest tip-off that you should use Lobito's rule is the question will say, use L'Hopital's rule. Okay? If the question says use L'Hopital's rule, you'd better use L'Hopital's rule. And the converse is also true. If the question doesn't say use L'Hopital's rule, don't use it. That's my advice. Or at least think really hard. Or maybe even raise your hand and say, should I use L'Hopital's rule? Just to, I mean, probably we won't say anything, but we might. We might be like, does the question say to use L'Hopital? We might be sarcastic with you, and that should be a tip-off then that you shouldn't, you know? Use L'Hopital's rule. So if the question says to use it, use it. If it doesn't, probably don't. Probably. I mean, I'm not giving you 100% on that. All right, so some indeterminate forms. All right, so let's write this down. This is a kind of a neat idea. Indeterminate forms. Okay. So what this is it's a bunch of like shorthand notation for situations where L'Hopital's rule is probably a good idea. Not always a good idea, but probably a good idea. So the first one is you write down 0 over 0. And really, I should put all these in quotes because these are just symbols. We're not really dividing by 0 or anything. You're just writing down some symbols to remind you that, hey, that's what happens. So 0 over 0. Okay, this is great. I'll give you, instead of like, so an example. Limit as x goes to 0 of sine of x over x. This is a 0 over 0 indeterminate form. Look at this. So as x goes to 0, what does sine of x do? And what does x do? So maybe this is a time to use L'Hopital's rule. All right, that's what we're doing here. So I'm just going to list all the indeterminate forms first, and I'll give an example. I'll list and I'll give an example. Hopefully I'll give an example. I'll try. Okay, the next indeterminate form is infinity over infinity. Infinity over infinity. Do I yell awesome? So here's my example. Limit as x goes to pi over 2 from the right of secant of x over tan of x. And if you look at this, this is an infinity over infinity. And of course, look, when you're doing this, you'll have a graphing calculator, right? And you'll be able to plot these things and see what happens. So that will help you out to know what's going on. And hopefully the question will say, use L'Hopital's rule. And say, I have to use L'Hopital's rule. Okay, what's another indeterminate form? We have all these indeterminate forms. Okay, let's see the next one. Yep. Don't get ahead of yourself, Bart. Yeah. 0 times infinity. 0 times infinity. All right, now this one's a little harder. Okay, so this would be like limit as x goes to 0 from the right of x natural log of x. Now, do you see a fraction here? I don't see a fraction here either. But we'll show you how to get a fraction out of this. This is not something we can do with L'Hopital's rule, okay? No fraction. This is a harder one, okay? So that's a harder one. Okay, here's another one. Infinity minus infinity. Okay, so that would be like something's getting big and something else is getting big, and you're subtracting them, and hopefully the infinities somehow mysteriously cancel out. So an example of that would be limit as x goes to 0 of cotangent of x minus cosecant of x. Oh my God. Okay, so now we got that. Oh, that's not so bad. Okay, that's infinity minus infinity. Yep. Looking good. Do we have any more? Oh, yes. Okay, there are between 1 and 4 more. So here they are. There's 1 to the infinity. There's 0 to the 0. There's infinity to the 0. Oh, sorry. There's between 1 and 3 more. And these are all done the same way. These are all done the same way. And an example of that would be like this. It'd be limit as x goes to infinity. Oh, geez, Bart, come on, right. X goes to infinity of 1 plus 1 over x to the x. Let's see, and which one is this? This looks like as x gets really big, this thing here goes to 1, and the exponent goes to infinity. Does that make any sense to anyone? Nobody's saying anything. Oh, a few people are nodding. Okay. So these are our indeterminate forms. Okay, let's try to use L'Hopital's rule to calculate some of these. I guess I'll say one more thing. Your book makes a big deal out of the fact that 0 to the infinity is not an indeterminate form. Oh, let me just tell you what okay, so I said these are all indeterminate forms, but I never really told you what that meant. I'm sorry. My apologies. What it means is that, hey, look, this thing's going to 0, this thing's going to 0. I'm not sure, it's not real clear to me what the limit's going to be, right? If the numerator is going to 0 and the denominator is going to 10, what's the limit then? 0, right? If the numerator is going to 15, the denominator is going to 3, what's the limit? It's 5. It's easy. Here, I just don't know. Indeterminate. It means I just can't figure it out. 0 to the infinity is not indeterminate, because what happens when you raise 0.5 to a high number? It gets smaller and smaller and smaller and smaller. So for any value near 0, when you raise it to a big number, it just goes, so when you have a limit that looks like this, it just goes to 0. So that's not really an indeterminate form. All right, so let's try to beat these problems with L'Hopital's rule. I'm going to run through and try to do one of each example. I'll do 2 of these. Okay, so sine x over x. This is in some sense a bad example, because the way that you know how to compute the derivative of sine x, you had to know how to compute this limit to begin with. We're going to do it anyways. Okay, so the limit as x goes to 0 of sine of x over x. The L'Hopital's rule says, plug in 0. What do we get? This is of an indeterminate form, 0 over 0. So I can look at the derivatives. What's the derivative of sine? Cosine of x over, the derivative of x is 1, right? And what's cosine of 0? 1. So this is equal to 1. Now, I don't know, does L'Hopital's rule kind of seem like magic? Okay, it should kind of make sense, because the idea is if both of these are at the same value, right? So I have 2 functions, and they're both 0 at some point. And then I say, hey, and they're growing at the same rate, right? Remember, sine looks like, if I can, this is a mystery. I think, there's lots of options. I'll be right back. Just run up here. And I think, that is a mystery. Where did I put my chalk? Oh! If I just use my eyeballs, I can find the case. Okay. Whew, thank you. It was a mystery to me. So here is, there's sine, right? And here's what And I've drawn this picture for you guys before. There's what x looks like, right? Of course the limit's 1 when you look at the picture. Okay, so that's the indeterminate form 0 over 0. If you ever have to do a L'Hopital's rule problem, you hope to find this one. However, you probably won't. It will probably be one of these terrible ones that comes up next. Okay, so now let's do the next one. Let's do the infinity over infinity one, where it's limit as x goes to pi over 2 from the right of secant of x all over tan of x. Okay, in this case, let's see. What is secant? What is secant? What? No, I'm just asking what it is. It's 1 over cosine. So secant of x is equal to 1 over cosine, and tan of x is equal to sine of x over cosine of x. Okay. Whoa. X. There we go. Cosine of x. Otherwise, it's nonsense. Cosine of pi over 2, right? Is, let's see, cosine of pi over 2 is going to be, what's cosine of pi over 2? 0. And as we approach pi over 2 from the right, draw a unit circle. I'm approaching pi over 2 from here. Cosine is, it's negative until it gets here. So this is going to equal negative infinity. And sine of pi over 2 is close to being 1, right? And then we're dividing by things that are closer and closer to negative and 0, right? So this is also going to be, don't equals, goes to negative infinity. Okay, well this is perfect for L'Hopital's rule here. Okay, so if I call this one f of x and I call this one g of x, f prime of x, derivative secant is secant of x tangent of x, and the g prime is equal to secant squared of x. Is that correct? So by L'Hopital's rule, what we should do is we should look at the fraction now. And this fraction is kind of nice because now the limit as x goes to pi over 2 from the right is going to be secant of x tangent of x all over secant squared of x. And now we cancel, right? And so this is equal to the limit as x goes to pi over 2 on the right of, well, one of these secants is going to cancel. And secant is 1 over cosine, right? 1 over cosine of x. And tangent is sine over cosine. I think that's the only thing I know. Over cosine of x. And so what's going to happen now? Yeah, these are going to cancel. These cosines here will cancel, and I'll be left with this is equal to the limit as x goes to pi over 2 from the right of sine of x, and even I can calculate that. That's equal to 1. What questions do you have about this? Is this okay? Yeah. I don't know. Maybe this is a stupid example. Let's go ahead and see what happens. Okay, what are you going to say? Okay, so we have two conflicting questions here. I think your question is after this point right here. Yeah, you could. But I don't think so. Yeah. And you get sine of x at the end. But this guy's question is, hey, Bart, why were you being so silly in the first place? And he says, maybe you can just simplify this. So he says, what do you want me to do again? You want me to write 1 over cosine of x? 1 over cosine of x. This is equal to the limit. Let's see, I don't know, maybe this is a bad example. Pi over 2 plus cosine of x. 1 over cosine times tangent of x, which is equal to sine of x. Oh, this is you're right. He's right. Wait, no. Yeah, this isn't hard to read at all, people. Okay, cosine of x, because it's 1 over tan, sine of x. Cosine of x, sine of x. And then he says these cancel, then it's 1 over sine x, and then you're done, right? Yeah, this is I'm sorry. I'm not going to do a better example, okay? But this is you're right. You could have done this without L'Hopital's rule. Okay, I apologize. Okay, I'm sorry. But we're just going to keep on going, okay? Because we got more. This is not the sort of thing that's going to cause you guys problems. If you guys see something like infinity over infinity, you're just going to take the derivatives and go on your merry way. All right? That's okay. I'll make a note that this is stupid. Stupid, Bart. Thank you. Okay. Let's do an example of x natural log of x here. And maybe somebody can explain to me why this example is stupid too. Okay. Can I erase the statement of L'Hopital's rule? Basically, what are you looking for? A fraction. What do? Take the derivative of the numerator, take the derivative of the denominator. Do you use a quotient rule? No. That's why it's so great. You don't have to. Okay? If you had to, that would be terrible. You should not expect to see a fraction when we give you L'Hopital's rule. I would love to give you a problem with a fraction. But it should be, you should be like, okay, they're not going to give us something so easy. All right? So this is 0 times infinity somehow. So we have the limit as x goes to 0 from the right of x natural log of x. All right. So this is something very small. So as x goes to 0 from the right, it's something very small. And this is something very large and negative, right? And so here's the idea. X natural log of x is equal to natural log of x over x to the minus 1. The trick is always the same. If it doesn't look like a fraction, make it look like a fraction. It's always the same here. Now, what does natural log do as x goes to 0 from the right? It goes like that, right? To negative infinity. What does 1 over x do as x goes to 0 from the right? It goes to positive infinity. Now we're doing an example like the one I said we weren't going to do of infinity over infinity, and maybe this one isn't as stupid as the last one, okay? Let's find out. Okay, so I'm going to set f of x equal to natural log of x, and I'm going to set g of x to equal x to the minus 1. And now f prime of x, that's the derivative of natural log, is equal to 1 over x. And g prime of x is equal to minus 1 x to the minus 2, right? Minus 1 x to the minus 2. That looks great. So now, this, oops, not that. This here is equal to the limit as x goes to 0 plus 0 from the right of f prime of x, 1 over x, over minus 1 x to the minus 2. Now, I know this is confusing with all our negative exponents and everything, but we're tough and we're smart enough that we can figure this out, I think. I think I am, at least. Limit as x goes to 0 from the right. That's going to equal this 1 over x can be put in the denominator, and so this is going to be minus 1 over x squared, right? Is it okay? Yeah. Can you just take the derivative of x, natural log of x, and get the same result? Well, that would be an accident if it gives you the same result. You just can't take the derivative of a limit and hope that it gives you the same thing, right? For example, the limit as x goes to 0 of sine of x is equal to 0. But if I take the derivative of sine, I get cosine. So it changes the limit. Did I answer your question? Yeah, you just can't. It would be nice if you could. That would simplify things. So we can simplify this further. This is not equal to the limit as x goes to 0 plus of minus x. And then what's this thing here is equal to 0. So our limit's equal to 0. If you wanted to check your work, how could you check your work? Because you can. With all these problems, there is no excuse for you having the wrong answer. You should always have the right answer, which is why having the right answer isn't so promising. But I mean, isn't so like yay! But you guys should always have the right. How do you just get the right answer? You graph it. You should, if you want to know, did you do it right? Graph it. They'll tell you if you got it right. Assuming you graph it correctly, right? All right, so this is the first of the kind of weird Lobitals. And what was the trick? We took something and we put it in the denominator. Could we have put natural log in the denominator? Yeah, no problem. I don't think anyways. What would have happened? Hold on. 1 over x. 1 over x. You're gonna have. I don't think it would have caused a problem. I don't know. Does anybody, let's not, if you're curious, try to do it the other way. That's what you should do. Do you know what I'm talking about? Yes or no? That's a very unconvincing yes. All right, so now, let's do the next indeterminate form. If we have time, we'll come back and we'll try to do this one the other way. And then I'll also show you something that L'Hopital's rule doesn't work for. But okay, so this is infinity minus infinity. Oh yeah, we have a couple examples of this one. Okay, so the first one is the limit as x goes to 0, this crazy trig stuff. Cotangent of x minus cosecant of x. Yeah. Anybody have any ideas how to do this one using L'Hopital's rule? What do you need to do L'Hopital's rule? You need something. You have to have a fraction. Without a fraction, you are stuck. Okay? You can't do anything without a fraction. Is cotangent a fraction? Yes. These are fractions. So the first case for infinity minus infinity is we give you some trig stuff that's a fraction, like tangent or cotangent or cosecant or something like this. And cotangent is equal to cosine of x over sine of x. Please don't be too hard. Minus cosecant 1 over sine of x. Whew, I think I can do this problem. All right, and now this is equal to the limit as x goes to 0 of cosine of x minus 1 over sine of x. Awesome. Okay, so now, as x goes to 0, sine of x goes to 0. As x goes to 0, cosine of x goes to 1, so the numerator also goes to 0. So this is the indeterminate form, 0 over 0. Okay, I can handle this. I just set f of x equal to cosine of x minus 1. G of x is equal to sine of x. And now I take the derivatives. Okay, derivative mode. F prime of x, derivative of cosine is negative sine minus sine of x. And the derivative of g of x is, derivative of sine is cosine of x. And so this terrible limit here is equal to the limit as x goes to 0 of minus sine of x over cosine of x. Now, you might be really tempted to convert this into negative tangent right away. Don't do it. There's no point. All right? Because what you should do is you should say, well, what happens as cosine goes to 0? You get 1. What happens as sine goes to 0? You get 0. So this whole thing is equal to 0. Converting it to tangent wouldn't have helped you unless you are really one with tangent and know tangent really well, which maybe you do. By the way, I'm just going to keep on talking. If you guys have questions, just shout them out. I don't care. Okay, do you have any questions? Okay, what questions do you have? All right, here's the other infinity minus infinity indeterminate form. Here's the other infinity minus infinity indeterminate form. There's, at least as far as I know, there's only 2 ways these come up. Maybe there's another one. If you find more, you can send me an email. Infinity minus infinity. Here we go. The limit as x goes to infinity of the square root of x squared plus x minus x. Okay, so as x goes to infinity, this thing here is going to go to infinity, right, as x goes to, and this thing here is also going to go to infinity. What's the trick here? Oh, yeah. Okay, here's the trick. I used to tell myself this. In my youth, I thought this was a good idea, but I'm not so sure anymore. When in doubt, factor. Okay? I'm not sure if that's a good idea, so maybe you shouldn't write that down. But he's telling me it's a bad idea. Anyways, here's what you should do here is factor. You should try to factor out an x from everything. So this is equal to the limit as x goes to infinity of, well, I can factor out, I could do something here. I can factor out an x squared here. And so this is the square root. I'll do this really slowly of x. That's kind of unlike, I don't know. Okay, 1 minus 1 over x minus x here. You guys agree with this? You might say, how did you know to do that? The answer is, that's what you do. All right, yeah. He wants me to multiply by the reciprocal You get a fraction on the bottom. Natural. Yeah. He wants me to multiply by the conjugate that equals 1 and get a fraction. Yeah, sure, why not? Yeah, your way's fine. Well, let's do it both ways. Okay, so first we'll do it this way. Let's just see what happens. We'll do it my way first, and then we'll try the conjugate. Conjugate's always a good idea. We're not doing the conjugate right now. This is just to remind me so I don't forget, because by the time we're done with this problem, I will have forgotten everything. Okay, so this is equal to the limit as x goes to infinity of, I can factor out the x times the square root of 1 minus x, and this is equal to, the limit as x goes to infinity of x times the square root of 1 minus 1 over x minus 1, like so. We've reduced it to a case we've already done. We've already done 0 times infinity. This is 0 times infinity, all right? And so what I'm going to do here is I'm going to do the exact same trick. I'm going to make this look like a fraction by rewriting this as equal to the limit as x goes to infinity of something over x to the minus 1 right here. So now I have the square root of 1 minus 1 over x minus 1. And so now yes? Why is it all of a sudden under the radical minus instead of plus? That's a good point. You just can't see these pluses. No, I'm sorry. Yeah, it's a good point. Thank you very much. Thank you. I'm sorry. Yeah. He says, how did you go from this x to this 1 here, right? Okay, so to do that, I have this x here and I have this x here. And what I'm going to do is I'm going to factor out that x. So when you distribute this, it'd go to both of those. Did I answer your question there? I'm sure other people had that question too. All right. So now we're in a position to use L'Hopital's rule because it looks like a fraction. That's what we're trying to do the entire time. Looks like a fraction. Oh, yeah, I got to say f of x is equal to the square root of 1 plus 1 over x minus 1. G of x is equal to x to the minus 1. So f prime of x is equal to, oh my goodness. Oh, you can do this part. Okay, so 1/2 times 1 plus 1 over x to the minus 1/2 times the derivative of the inside, which is equal to minus 1 x to the minus 2. Yeah, that's right. And now g prime of x is equal to minus 1 x to the minus 2. Which is super convenient, right? Because we're going to write these as a fraction here in a second. And guess what's going to cancel immediately? Yeah, those x to the minus 2s that we don't really want to deal with, right? So so the limit as x goes to infinity of f prime of x over g prime of x. I'm just going to cancel it right now. It's equal to the limit as x goes to infinity. This is going to cancel with this here of 1/2 times 1 plus 1 over x to the minus 1/2. What's this limit equal to? Limit as x goes to infinity of 1/2, 1 plus 1 over x to the minus 1/2. As x goes to infinity, what's 1 over x go to? Okay, as x goes to infinity, here, 1 over x goes to 0. So 1 plus 0 is 1. 1 over the square root of 1 is 1. Times 1/2 is equal to 1/2. There's our final answer. Now the question we got at the very beginning was, Bart, maybe it's not easier. Maybe it's easier just to multiply by the conjugate because we love doing that. That's a really great idea. Let's see if we can just plow through that really fast and see what happens. See if we get stuck. If we get stuck, we'll give up because we already know how to solve this problem. But if we don't get stuck, we'll just say, hey, that's a good idea. All right? Conjugate's a great idea. Okay, so here we go. We have the limit as x goes to infinity of the square root of x squared plus x minus x. And this guy says, hey, I want you to take this and multiply it by the conjugate over itself. So that's going to be a square root of x squared plus x all over square root of x squared plus x. Okay, seems like a great first move. Okay, and so what you're going to do is then this is going to be the limit as x goes to infinity. This might be a much better way to do it. I have no idea what's going to happen. X squared plus x is in the denominator. And in the numerator, you're going to have x squared plus x minus x squared. Isn't that right? You get the difference of 2 squares, right? Okay, well, that sounds nice. For one thing, these are going to cancel, right? And so maybe we can just use L'Hopital's rule at this stage here. Limit as x goes to infinity of x over square root of x squared plus x. Let's see. This one goes to infinity. This is infinity over infinity. Okay, what's the derivative of x with respect to x? That one was easy, right? So this should be equal to, I'm just going to do this all in one step. X to infinity, 1 over, okay, this is looking good to me, folks. The square root is going to be 1/2 times x squared, oh geez, this is kind of crummy, to the minus 1/2 times 2x plus 1. I'm doing the chain rule, right? You guys got to be pros at these derivatives. If you can't do them, practice. Practice. Plus 1. Oh, geez. Oh, no. So what you have here is you got 1 over a square root in the denominator here. Well, it's not so bad, actually. You can make it work if you want to grind through it, okay? You can really make this work. But it's what probably the better step than just kind of blindly applying L'Hopital's rule is factoring out the x here and then canceling. And that would have made your life a little easier. But let's not go. We've already solved it one way, and we did that trick. If you want to know how to do it, you can talk to me after class, and I'll go through it all again in painful detail. Okay? All right? Okay, so let's see. How much? What other? Well, that's it. Oh, we only have one more indeterminate form to do. Great. One of these. And the problem we're going to do is this one right here. Does anybody know what this limit's equal to? Limit as x goes to infinity of 1 plus 1 over x to the x? Anybody know? Any guesses? Equal to 1 maybe? 18? 22? Okay, let's see. Let's see what we get. Yeah, how the heck am I supposed to I think, oh yeah, yep, of course. Okay. Limit as x goes to infinity of 1 plus 1 over x to the x. You always do the same trick here. You want to convert this into something else. And so what you do is you say, well, this is equal to e. Oh, sorry, this is equal to the limit as x goes to infinity of e to the natural log of 1 plus 1 over x to the x, like so. Now what you do is you just forget about the e and the limit for a while. You say, okay, well, now what I'm going to do is I'm going to focus my attention. E is a constant, so really the only thing that really matters right now is the stuff in the purple box. That's all that matters. So let's pay attention to this and see what happens. So looking at the stuff, look at the purple box. Look at the purple box, and what do we have? We have the natural log of 1 plus 1 over x to the x. And when I have natural log of something to a power, what can I do with that power? Bring it down, right? And so now, look, this looks a lot like an example that I did earlier, this one, right? X to the natural log of 1 plus 1 over x. And what was the trick with this problem? What did we do? Yeah, 1 over x to the negative first. See, we're doing the same trick again and again and again. So let's see. We're going to write it as 1 over, as natural log of 1 plus x. So we have a fraction over x to the minus 1. That's this x right here. And we have natural log of 1 plus 1 over x. I think that's right. Okay, and now what I want to do is I want to take this limit, because again, to understand this limit, I really need to understand the limit of the numerator. So I'm going to take the limit as x goes to infinity here. We still have a problem, all right? Natural log of, oh, maybe we don't have a problem. What is, let's just use Lobito's rule anyways. Wait, what's natural log of 1? And oh yeah, and this is equal to, remember, x to the minus 1 is equal to 1 over x, right? And so as x goes to infinity, the denominator also goes to 0. Okay, so we can do it. We're doing great, guys. X to the minus 1. Okay, so use L'Hopital's rule, take the derivative of the numerator and the denominator. This is equal to the limit as x goes to infinity of, well, the derivative of the denominator is minus 1, x to the minus 2. And the derivative of the numerator, there's that trick you can do with log, right? Yeah, and what you do is you just do something over the thing inside, right? And then you put the derivative on top, right? The derivative of this thing. And we've been taking the derivative of 1 over x like we got like 3 minutes. We've been taking the derivative of 1 over x like a billion times. It's minus 1 over x to the minus 2. Oh, holy cow. These things are going to cancel, right? And so this is equal to the limit as x goes to infinity of 1 over 1 plus 1 over x. What is the limit as x goes to infinity of 1 over 1 plus 1 over x? It's just 1. That means that this is equal to the limit as this. That means this is equal to the limit as x goes to infinity of e to the 1. What's e to the 1 equal to? E. The limit as x goes to infinity of 1 plus 1 over x to the x is e. Who knew?